Would you like to know the story of voltages in digital system? What are the different voltages used in digital systems, including processors and controllers? How are these voltage levels decided? Are all the voltage levels compatible to each other? How should we connect systems of different voltage levels to each other? In digital systems, voltages are ideally at logic 1 equivalent to 5 volt or at logic 0 equivalent to 0 volt. But the story is not simple as it appears. The answer lies in the foundation of digital system. The building block of a digital circuit is based on transistor-transistor logic, abbreviated as TTL, or complementary metal oxide semiconductor, abbreviated as CMOS logic. All the TTL based logic gates are constructed using bipolar junction transistors, in short BJTs, having 3 layers of semiconductor with different nature of doping and hence 2 different variants. The terminals are emitter base collector biased with different voltages. The CMOS based logic gates are constructed using metal oxide semiconductor field effect transistor, in short MOSFET, having semiconductor layers with appropriate doping and metal contacts serving as terminals. Transistors are combined properly to create functioning of logic gates. When logic 1, that is high state of voltage, is applied to 2 inputs A and B of the emitter side of transistor Q1, the next transistor at the output stage becomes on. Current starts flowing through the collector side resistance R2. The voltage drops in R2 and output becomes 0, the low level of logic. The complete truth table reveals a particular combination of input and output. The corresponding circuit behaves as NAND gate. There are other truth tables for OR and NOR gates, NOT gate, XOR and XNOR gates, and NAND gates along with. But the presence of noise superimposed on the gate voltage creates undesirable change of voltage state. The problem is aggravated when multiple gates are interconnected. The voltage swing may appear at various nodes. The allowable voltage swings are different for gates constructed with different technologies. Now we will investigate the tolerance of voltage for TTL gates, especially when the power supply to the gate is 5 volt, and we investigate the tolerance at the input terminal. Our 2 to 5 volt is treated as high or logic 1. The state low or logic 0 is considered when input voltage is 0 volt to 0.8 volt. The specification is tighter at the output side. Voltage between 2.7 volt and 5 volt is considered as high or logic 1, and voltage between 0 and 0.5 volt is treated as low or logic 0. Here is the comparison of voltages at both of the sides. Obviously, the acceptable tolerance of voltage is higher at the input side. This means the logic gates are more flexible to the voltage swing at the input terminals. The noise margin of a logic gate is defined as the difference between input and output range. The minimum voltage required at the input for which it will be treated high is called VIH min. The maximum voltage permissible at the input for which it will be treated low is called VIL max. The minimum voltage required at the output for which it will be treated high is called VOH min. The maximum voltage permissible at the output, for which it will be treated low, is called VOL max. The difference between the two permissible values of voltages at high state is called high level noise margin. For low state, this difference is called low level noise margin. Now we consider voltage tolerance for CMOS gates. The power supply is considered as 5 volt. For high state, the tolerance is 3.5 volt to 5 volt. For low state, it is 0 to 1.5 volt. Here is a comparison of allowable tolerance between CMOS and TTL gates. The output voltage of CMOS gate, however, has tight specification. The corresponding high-level noise margin can be estimated. The estimation can equally be applicable to low-level noise margin as well. Same nomenclature is used for voltage levels of CMOS-based gates. Obviously, the noise margin is better in CMOS compared to that of TTL. Now, we would like to investigate the effect of power supply voltage on noise margin of CMOS-based gate. The power supply is considered as 5 volt, 10 volt and 15 volt for illustration. When the power supply is at 5 volt, the noise margin is 1.45 volt for high level as well as for low level. When the power supply is 10 volt, the noise margin goes higher to 2.95 volt in each case. In case power supply is enhanced to 15 volt, noise margin is even larger with a value of 3.95 volt. Hence, in all cases, permissible input swing is more than output swing. Greater the power supply, higher the noise margin. Higher the noise margin, more is the prevention of false triggering of logic state by a noise. The rejection of noise therefore is better. CMOS gate is designed also to work on 3.3 volt. Here is the corresponding noise margin. A 2.5 volt CMOS logic is also available in practice. A further lower level of 1.8 volt is used along with. But why is the decreasing trend of voltage in real field? It is due to less power consumption, smaller chip area, smaller signal swing, and less switching noise. Let us investigate the sources of power consumption. Obviously, it has various causes and types. Every MOSFET has a capacitive effect. The capacitors are charged and discharged in every switching cycle. The corresponding power loss depends on the clock frequency, value of load capacitance, and the number of switching taking place per cycle of clock, called activity factor. Obviously, the switching loss heavily depends on power supply voltage. The short circuit power loss takes place when there is a transition of input signal. One gate is going to be on, the other gate is going to be off, and there is an overlapping of their on state for some time, whatever small the time may be. Its magnitude depends on the transition time and the peak current of the circuit. But its dependence on power supply is again observed. The static power or leakage power appears with the decreasing size of the transistor. With reducing size, oxide layers get thinned. Probability of electrons to penetrate layers increases Hence, leakage current increases. As a whole, power consumption reduces when power supply voltage decreases. But there are disadvantages of decreasing voltage also. When the supply voltage is considerably higher than the threshold voltage of MOSFET, its own resistance decreases. The RC time constant of charging and discharging reduces. The delay of attaining logic state reduces as the charging and discharging becomes faster. As a result, switching frequency can be increased. With enhancement of operating voltage called overvolting, both of the power consumption and switching speed become high. Due to undervolting, on the other hand, both become low. The optimum condition for attaining good switching speed at lower power loss is a matter of requirement and design. A power management technique called dynamic voltage scaling is often applied to processors, controllers, and peripheral devices. However, the level of voltage can be shifted during peripheral interface by designing systems with appropriate ICs and circuits.